this very first section, 8.1. This is a very important section because we sort of walk you through step by step the basics of hypothesis testing. And then what you learn here pretty much can be directly applied to 8.2 and to 8.3. So we'll talk about that in a little bit. But before we get into this hypothesis testing, I actually want to scroll down a little bit to page 3 here. And there's I think a visual that will help you understand exactly what's going on in Module 8. And so here is a graphic that you should be a little bit familiar with. This should look familiar. This was a normal distribution, right? So we talked about a normal distribution, and this normal distribution happens to have a confidence level of 95%. So it's got a 95% confidence level. And in Module 7, we talked about how this was the lower boundary, this was the upper boundary, and the area in between them was the 95% confidence level. I don't even need to write this because it's typed right there, right? 95% confidence level, okay? And we spend all of Module 7 looking at confidence intervals. We would give you a confidence level, 95%, 90%, 88%, whatever it was, and you would find a lower bound and an upper bound that contained that area. And that's what we talked about in Module 7. Now, along with this confidence interval, we also talked about something else. We talked about a significance level. And we said that the significance level was the area under the tails. So if you had a confidence level of 95%, then the area under the tails, the significance level, was 5%. 2.5 under one tail, the left tail, and 2.5 under the right tail. This is what we're going to be looking at in Module 8. In Module 8, we are interested in the area under the left tail and the area under the right tail. This is called the significance level. And what you're going to do is you're going to establish a significance level. We're going to call it alpha. And so you're going to establish alpha. And for the sake of argument, let's just say that alpha is 5%. So we're going to say alpha, which is your significance level, that is the bar. And we're going to set our bar at 5%. So this is what we're going to do. And that's sort of what this graph represents. And now we're going to do a normal distribution. We're going to set a mean and a standard deviation, and we're going to look at some things, and we are going to find what's called a p-value. A p-value will be the area under the tail of the data distribution that we have. So let's pretend that this is some unknown distribution. Okay, so I'm going to black out the 95%. I'm going to black out these tails. Okay, so let's say that we do an analysis on our data, and it looks something like this. If this p-value, and again, the p-value is the area under the tail. So it would be this value here, and it would be this value here. If this p-value comes in greater than 5%, let's say that we find this area and this area, and they happen to be, the combined area is 8%. If our p-value is at 8%, that's bad. We've gone over our threshold, and we fail to reject the null hypothesis. We'll talk about what that means in a little bit. Just know that an area, a p-value above our threshold, is bad. It's kind of like in tennis, when you cross the line, it's called a foot fault. Or in bowling, if you've ever been bowling, there's like this line that you're not supposed to go over, otherwise you fault. That's what this alpha is. It's sort of the line that you don't want to go over. On the other hand, if we calculate the area under these tails, and let's say this area comes in at 3%, if it's below the threshold at 3%, that's good for us. We want to come in below that 5% alpha value, below the 5% significance value. This is good for us, and we get to reject the null hypothesis and replace it with our alternative hypothesis. Now I'm talking hypothesis and null and alternative and all this crazy vocabulary. That's what I'm going to explain back up at the top of this module when we get into the definitions and the vocabulary for hypothesis testing. Okay, but this is the idea. This is what we're going to do. Remember back in module 7, everything was about intervals. what's your lower bound and what's your upper bound. We had all kinds of different scenarios, but the bottom line was, what's your upper bound and what's your lower bound, right? That's what you were looking for, an interval. In module 8, everything's going to be about, are you above your threshold or are you below your threshold? That's what we're looking to find. That's the big picture. We're going to do all kinds of mathematics and use a little bit different vocabulary. But at the end of the day, the question is, are you coming in at 8%? And then that means something. There's certain action you have to take. Or are you coming in at 3%? And so that's what we're going to look at. We're going to be finding these P values, the area under the tails. Let's talk about, now that you sort of understand the big idea, let's go back up to the top and talk about some vocabulary terms to go along with this idea. Hypothesis testing. So hypothesis testing has been part of the scientific method for a very, very long time. Okay, so the scientific method says that when you make a hypothesis, an educated guess to explain something, hypothesis cannot be proven true, but instead it can only be proven not false so far. This is kind of a proof by contradiction. A scientific hypothesis is never proven true. It's only proven not false. In mathematics, you can prove things. If you remember like your geometry class from high school when you had to do proofs, remember like angle, side angle, and side angle, and all these different proofs, you could prove stuff abstractly in mathematics. You can't do that in science. You can't prove that gravity is true. All it would take is one experiment that shows that gravity is not true, and you've got a new model for gravity. And so this is the idea of the scientific method, and this is what we're going to be using hypothesis testing for. So an appropriate analogy is something like this. The existing hypothesis is kind of like King of the Mountain. Did you ever play King of the Mountain in elementary school? You know, like if you lived in Michigan, there's a big snowbank someplace and all the kids would get on the snowbank and one person would say, I'm King of the Mountain. And then somebody would come along and they go, boop, and they'd just push them off, right? And then that person became King of the Mountain until somebody else came along and pushed them off. That's what the scientific method is like. It's like a giant game of King of the Mountain. And the existing king on the mountain is called the null hypothesis. This is the historical value, the existing accepted claim. This is what we are hoping to prove false. We don't like the null hypothesis. We don't like the existing king on the mountain. What we would like to do is push the null hypothesis off the mountain and replace it with our alternative hypothesis. That would make us very happy. And that's what we want to do. That's the whole point of the scientific method, is you take a look at the existing theory and you try to come up with an experiment that pushes that theory off the mountain, and then you can replace it with your theory. And your theory will only hold until someone comes and pushes you off the mountain. This happened with, let's say, gravity. Okay, so you remember like Galileo a long time ago on the Leaning Tower of Pisa, as the urban legend goes, and he drops the two rocks and they fall at the same rate. And he's like, gravity. Okay. And so he kind of figured out that things fell towards the center of the earth, but he really didn't have a reason why, and he didn't have the mathematics to follow up. But Galileo's idea of gravity withheld for a long period of time until Isaac Newton came along. And Isaac Newton comes along and boop, just kind of pushes Galileo right off. And Newton says, this is why gravity works. It's because of the apple falling. And Newton actually invented calculus in order to explain gravity. Newton then is the new king on the mountain. And Newton ruled gravity for about 350 years until someone called Einstein came along. And Einstein looks at Newton and goes, boop, and pushes Newton off the gravity hill. And Einstein becomes the king of gravity because he talks about space and time and this curvature of space and the general theory of relativity, all this kind of crazy stuff that Einstein does. And he is the current reigning king on the mountain for gravity. Now, someone else could come along tomorrow and push Einstein off the mountain. And they could say, yeah, Einstein, you're close, but actually here's a better theory. This is how science works. Nothing is ever proven true. You don't say, you know what, Einstein, you got it right. It's all over. Nobody needs to study gravity anymore because Einstein's right. That's not how science works. Science is a perpetual, continuous improvement where you're king of the mountain today, but somebody else could come along and push you off with a better hypothesis and they become king of the mountain. These are the two players we're talking about, the null hypothesis and the alternative hypothesis. The null is the existing king of the mountain. That's what we hope to prove false and push off the mountain. And then our alternative hypothesis will come into play. There are three ways you can have this, and I'm going to draw this up for you in a graph. So here's your normal distribution, right? Boop, there's your normal distribution. And let's say that we've got some tails on this normal distribution. So here is the left tail. So I'm going to say left tail. Here is the right tail. And we've got areas calculated underneath each one. So that's our setup for right now. If you say that the null hypothesis is less than the claim, if your average is less than the average of the null hypothesis, mu of the alternative is less than mu of the null hypothesis. If this is the situation that you're claiming, then you look for the area under the left tail only. That would be less than. If, on the other hand, you think that your alternative is greater than, which would mean your mu is greater than the other one, you look at the area under the right tail only. And this is called a p-value, a probability value. So you have a p-value under the right tail and you have a p-value under the left tail. If it's less than, you take the area only under the left tail. If it's greater than, you take only the area under the right tail. Finally, if it is not equal to, then you take the area under both tails. Okay? And that's the area that you use to compare. If we have a threshold of 5%, let's say this is our alpha. This is our significance level. And we pick hypothesis number 1. We think it's less than. And so because we think it's less than, that means we are only interested in the area. Oh, there goes my curve. We are only interested in the area under the right tail. And let's say that this p-value comes in at 6%. Then what that means, 6%, means we foot faulted. We are above the threshold, and that is bad for us. That means we do not get to push the king off the mountain. The existing null hypothesis stays king of the mountain. On the other hand, if this p-value, if this area under the left tail comes in at 3%, then that's good for us. That makes us happy. That means we get to reject the null hypothesis and replace it with our alternative hypothesis until somebody else comes along and pushes us off the mountain. What are we looking for? What are you going to be doing a lot of? Finding areas under the tail of a normal distribution. That's what you're going to be doing a lot of. And then you're going to take that area and you're going to compare it to a threshold. And so we talk about that here. So in hypothesis testing, you're going to have a p-value and you're going to have a threshold or a significance, and you're going to compare these two values. And so we talk a little bit more about this. There is one more thing to talk about, the ethics of finding the p-value. So let's say, go back up to this example. Let's say that you think it's less than. And so you've got your left tail right here. Here's the area under this left tail. Let's say this p-value comes in at 5.2%. Okay, so let's say that's your p-value. So if our threshold is 5% and we come in at 5.2%, That's bad for us. That means we don't get to reject the null hypothesis. And let's say that we happen to work for a major university. This level one university gave us a grant for, I don't know, $20 million to do some research to develop an antibiotic that would help fight, I don't know, fleas on dogs or something. So the idea is we got a whole bunch of money to do some research, right? And our research comes in and it's not so good. It comes in at 5.2%, which means we don't get to reject the null. That's bad for us. We want to reject the null, right? And so you know what we do? We go back and we look at the data and we say, well, maybe we should eliminate this data because, yeah, that really wasn't part of the experiment. And let's add in some new data. And so we massage the numbers a little bit. And through this process of massaging the numbers, we get our p-value down to 4.8%. Oh, isn't that nice? And now at 4.8%, we are below our threshold. And yay, everyone's happy, right? This is called p-hacking. You are hacking the p-value. You set your threshold at 5%, and then you did your experiment. And your value came in above the threshold. And so you're going to go back and you're going to massage the data in order to come in below your threshold. This is unethical. You're not supposed to do this. And so if you want to find some interesting readings, go in and look up p-hacking. There is some ethics built into this type of experimentation because we're setting a threshold. We're saying, here's the bar. And you set that threshold before you begin the experiment. Then you do the experiment, you see what your p-value comes out to be, and if it's above the threshold, you fail to reject. If it's below the threshold, you reject the null. And again, we want our p-value to be below the threshold. So what is a good threshold to have? What should we set the threshold at if we're doing an experiment? 5%? Is that a good threshold? 10%? What about 1%? What about 7%? So in general, we're looking for a Goldilocks zone. We are looking for an alpha, a significance level that is rigorous enough where everyone's kind of like, yeah, that's legit, but not so rigorous that it's impossible to do. And so let's say you set your alpha at 1%, and I call this too hot. That means your threshold is 1%. That means when you do your data, this tail has to come in below 1% for you to reject the null. This is extremely difficult to do, very difficult to do. So while this 1% has extremely high rigor, like if you come in under 1%, nobody's going to question your experiment. They're going to be like, whoa, good job. You came in under 1%. That's amazing. However, it's extremely difficult to do. You have a much lower probability of rejecting the null. So maybe instead what we do is we crank it up because this is kind of tough to do. So let's set it at 10%. And this is what I call too cold. Get it? Papa Bear, porridge is too hot. Mama Bear, the porridge is too cold. So if we set this at 10%, well, that's really easy. Like anybody could come in under 10%. Like who couldn't come in under, hey, what was your alpha? 10%? Oh, really? Like who couldn't come in under 10%? And so this is very low rigor. It's not well respected among researchers. It's almost too easy. So 1% is too difficult. 10% is not difficult enough. So our Goldilocks zone is 5%. This is that 95% confidence interval that we talked about earlier. There's a reason why we spent so much time talking about 95%, because that's the 5% alpha value. And so this is medium rigor, like it's not as tough as 1%, but it's tougher than 5%. And you got a pretty good probability of being able to reject the null. And so that's where we're going to sort of settle on, is this 5% threshold. And that's the threshold that we're going to be using for the most part moving forward for the class. Okay. It may change a little bit, but 5% is just right.